going to start today and work through just basic Geon types of stuff here. First semester, working through our means based analysis, right? Our t-tests, our ANOVA models, things along those lines. And so we often think about these as univariate statistics, where we've just got one IV and one DV. Now, technically, our factorial ANOVA wasn't univariate because we had multiple IVs there, but to this point, this has kind of been the primary focus of our analyses. And so, problems with univariate stuff can sometimes be cumbersome, inefficient, right? If I want to know what the relation between gender and college performance is, well, I've got gender, but in terms of college performance, a lot of different ways to measure that, right? Performance can be defined by a lot of different things. We've got, say, course load, class attendance, hours, GPA, how much you like it, right? All sorts of different types of things that we could have. Now we've got a number of different outcome variables. If we're restricting ourselves to univariate statistics, that's a lot of t-tests, right? So some issues with inefficiency, but the big thing is it limits the types of questions that we can ask. What if I want to know the relation between trauma severity and psychological distress, whether or not men and women differ on post-trauma reactions, association between social support and PTSD? These are all fine questions to ask, but at some point they start to get kind of boring because they're limited in their overall scope. Okay? So our solution here is going to be our multivariate statistics. We're going to start combining multiple IVs, multiple DVs as we're moving forward with some of the stuff that we're going to be doing this semester. The multivariate statistics broadly talking about class of techniques looking at relations among sets of variables as opposed to individual pairs of variables, including multiple predictors, multiple outcomes. And this is an important thing. What we're doing with many of our multivariate techniques is sort of taking the associations between sets of different variables and using that to create more powerful tests. And we'll talk about in things like MANOVA and things like that, certain combinations of variables can start to provide more powerful joint tests than you might have individually across a series of outcomes. And the most important thing is what we can start to do is start to expand sort of the complexity of our research questions. This is going to result in more interesting, elegant research, right? So I can ask, what are the factors that might change the relation between trauma and trauma exposure and distress? What kind of question are we talking about here? Anybody have an idea? Not quite. Other one? Moderation, right? What are the third factors or fourth or fifth factors that start to impact this relationship? Increase, change the magnitude and the strength. We can progress and ask what types of factors account for the relation between trauma and prolonged distress, right? Mechanisms of action, what type of question is this? That's mediation, right? If we're looking at mechanisms, factors that account for the reasons why are related. And then looking at unique contributions of a number of different risk factors to the occurrence of PTSD, we're going to look at X1 to X5 and say, what are the unique relations of these variables to an outcome? This is a common question that we would use just in another standard multiple regression project, right? So we can start to ask more interesting and elaborate questions with our multivariate statistics than we can with our univariate tests. So got a lot of different models that we can use depending on what types of variables we're looking at, what types of outcomes, and the number of IVs and DVs starts to become complicated. How do we keep this all organized? This is one of the big things people start to get hyperventilated about. It's like, okay, these are the data I'm going to collect, how am I going to analyze it, what am I going to do to choose my model? At a very basic foundational level, your general linear model, this is your internal combustion engine of most of the statistics that you'll probably ever do, okay? Almost all things that we'll work on in this class and have worked on in last class, and things that you'll likely do in structural equation modeling, hierarchical linear modeling, things along these lines, These are all subsets and versions on that takes on the general linear model. Okay, so your GLM, broad statistical model encompassing a variety of different types of analyses. This is your common denominator. Okay, you didn't know it, but all last semester you were doing very specific, working with very specific subsets of the general linear model as you were looking at t-tests and ANOVAs, things along those lines. Okay. Basic familiarity with the processes of assumptions, characteristics, GLM. Going to do some things. One, help you organize your analyses, help you start thinking about, okay, these are the data I have, this is the question I have, how do I go through and put these pieces and parts together and choose an analysis that's going to be appropriate for my purposes. Also, as you start to, we're going to spend a lot of time talking about assumptions, using GLM assumptions, primarily within the context of a regression. If you start to get a strong handle on this stuff, other types of analyses that you would do, particularly like SEM types of things that are starting to become increasingly commonplace within our field, this is just an extension of this stuff. So if you get strong in the foundations, this is really going to help you pick up and start to understand some of these increasingly complex types of analyses. So think about basic assumptions of your GLM. Number one, linearity. Okay, linearity assumption, we're assuming that our pairs of variables in any analyses are going to hold some sort of linear relation with one another. Okay, basically what we're saying is that if I have X and I have Y, if I'm using a GLM, I'm assuming that a straight line adequately accounts for the relation between these variables. And if we violate this, what ends up happening is we either will fail to detect an effect, or the effect that we've estimated is going to misrepresent, underrepresent the true relation between these two variables. Okay, so here is some data. I don't know if they pulled out of Google. I don't know if it's real or not. But we're saying that this is the relation between a husband's age and a wife's age. What type of relationship do we have here? What do you think, Alex? What type of relation do we have here between age of spouses? What's that? Is it positive? Is this linear? Would we identify this as a linear relation? Yeah, absolutely, right? Pretty strong linear relation. It's incredibly strong, right? So this is a relation between two variables that certainly would meet our linearity assumption, right? We can draw a straight line through that, and that straight line does a pretty good job of accounting for the covariation between these two. What about this? What do you think, Katie? Is this, do we violate a linearity assumption here?
You can still kind of see it, but it's not strong.
Not as strong. It's not as strong. But if we go through, we've got drive ratio, horsepower. We're talking about cars here. A much weaker relation, but it looks like as horsepower increases, drive ratio decreases here, right? Not nearly as tight as the last graph that we had on there, but still certainly not violating our linearity assumption. What about this? So we've got education and income. We have a violation of linearity assumption here, Sam?
I sort of see it. Sure. No.
Okay, sort of depends, right? This is a little bit tricky. You're right, I see something that looks maybe like a curvilinear relation, right? And a curvilinear function is going to fit these data better than a linear function is. If I get a linear function, it's going to do maybe something like that, right? But it's looking like if we just plot these data out, and this is why we're always going to screen our data and take a look at the relations we have, it looks like there's a pretty strong curvilinear relation here. Now, the question is the added complexity that we would introduce into this model by introducing a curvilinear relation, what we get, does the variability in our outcome that we add by modeling this as a curvilinear relation, is that worth the added headache of having that? Or, as you suggested, Sam, would a straight line be a good enough approximation for this relation, right? This is both a statistical question and a conceptual question. If I think that education and income follows a true curvilinear function, right? Like this is an actual thing that's driving this relation, then yeah, I should probably model this consistent with my theory. But if this is just some random data and I don't have a strong theoretical reason to think that there's some sort of exponential function going on here, I could include that in my model, but it's going to make it a lot more complicated in terms of trying to talk about this. I might say, well, it looks in this specific sample, there might be a curvilinear pattern, but I don't know if that's actually representative of the population in general. And so what I'm going to do is I'm just going to model a straight line here, right? Now, what happens if I model a straight line when there's actually a curvilinear function there? Is my straight line going to be as good a fit as the curvilinear function? No, right? And so what I'm going to do is I'm going to underestimate the true relation between my x and my y if I'm forcing it into a linear pattern when there's actually a curvilinear piece to it. But the question is this worth sort of the added headache of modeling this in and explaining to people what's going on and trying to justify all this? That is going to be a study-specific situation. Okay. All right. What about this? Violation of assumption, linearity assumption here? What do you think, Morgan?
Yes.
Is it?
Well, it's just all over the place.
It's all over the place, right? So am I any worse off fitting a line to this versus any other such function?
No, you're not really going to have a line of best fit here.
Well, line of best fit is going to be flat, right?
Okay.
And so this is the thing. This, what type of relation do we have here? What do you think, Angeline? There isn't
There
one.
isn't, yeah.
There isn't one, right? So it doesn't matter. Like, up for grabs. Whatever that we want to try and fit to that is it's all going to fit the same, right? There's nothing there. This is complete static, right? And so while there's no linear relation between these two, we're not worried about a violation of linearity because there's not something else going on here. It's just random static, right? So this would be a zero correlation between x and y, right? So we haven't really violated linearity assumption because there's not a better fit. We're not missing anything here. It's just the best fit line is just a straight line. Okay. So, oh, did I miss that? So I've got a. Yeah, we'll get to that later on. Maybe not. I don't know. There's a cool online game that so you can guess the correlation. It's fantastic. I will send you the link. You can play. It's hard, right?
It's really hard.
It's hard.
It's surprisingly hard.
Yeah, and it's surprisingly entertaining. I'll send it your way. Bonus points for whoever gets the best score. Not really, but I don't know. You guys are cheating or what? But okay. So this is our linearity assumption here. All right. Second assumption is an assumption of additivity. Additivity assumption says that as we include additional predictors into our model, think about a regression model. So we have one predictor that accounts for some proportion of variability in our outcome. And then what we're assuming is the second predictor that we add in adds something above and beyond the first, and the third adds something above and beyond the combination of 1 and 2, and so on and so forth, right? In a perfectly efficient model, our predictors of whatever outcome we're looking at would be uncorrelated with one another, right? That's our most efficient model. That's often not what we're working with in applied psychology because everything's related to everything. But in a perfectly efficient model, our one predictor would account for this piece of our outcome, our second predictor would account for this piece, our third predictor would account for this piece, and if our predictors are all unrelated with one another, there's no crossover, right? What ends up happening is we'll spend a lot of time talking about this. What ends up happening is our predictors are in fact correlated, and so what we end up with in our regression coefficients is predictors looking at the unique relation. This is the unique piece of my outcome that is attributed, that is sharing covariance with this predictor that's not shared with anything else, right? And then this, when I add this other one, this is the piece that's uniquely related to this, and so on and so forth. consistent with this assumption of additivity. Questions about additivity? Linearity is pretty straightforward in terms of visualizing things. We will kind of get the idea of what we're going for in terms of an additive model here. So basically what we say, if we plot out this regression equation, right? X1 plus X2 plus X3, we can actually see this going on. So we've got this piece of things, and then we're adding a weighted component of the second predictor, and then an added weighted component of the third predictor, so on and so forth. Okay. So what does this, our GLM look like? There's lots of complicated stuff in there. Luckily, we don't have to worry about the underlying, because I'm not going to make you worry about underlying mathematics and things like that. At the very basic bivariate level, our GLM takes the form of a basic linear function here. Okay. If we're asking what the relation of depression is to post-trauma symptoms in community survivors with PTSD, sample of 208, right? What we want to do is look at the relation between two variables within the context of a general linear model. And so, can someone tell me what our y hat is here? What do you think, Angeline? Yeah, we'll say post-traumatic. We could go either way, right? But our predicted value based on our model, right? That hat says that this is not necessarily an observed value, but it's a predicted value. This is going to be our intercept, and B is going to be our slope, and then that X is our variable. In this case, we'll call this depression. Okay. If we actually run this out, we get our predicted value. Our intercept here is 24.8. Our slope is equal to 1. Okay. So given this equation, what is our expected value of PTSD when depression is equal to 0? What do you think, Katie?
24.
Perfect. How did you get that?
Plug 0 in for
High five, yeah, exactly right. Way to use math, right? No, this is the thing, right? Like, so our intercept is our expected value of our outcome when our predictor is equal to 0. That's always what that's going to be, right? And if we go through and plug 0 in for our PTSD value, that goes away, and this is what we're left with, right? What about this? What, Lauren, is our expected change in PTSD given a unit change in depression? What's that?
I said, where do you plug one? Do you plug one in?
Yeah. So given a unit, so if we were to increase our depression score by 1 unit, how many units would we expect our PTSD score to increase by? Cut it in half.
Oh.
1.
Okay.
Right. This is our coefficient, our slope right here, right? And this actually turned out to be. Like I ran these data just because I had it, because I'm like, oh, I need to plug something in there. I was like, pulled up a random set and ran it, and I was like, oh, the slope is 1 exactly, which was weird. But so for this measure, for every unit we see an increase in our depression score, we expect a corresponding unit increase in our PTSD score, right? And we get that out of our slope. So when PTSD is equal to 0, we expect our depression is equal to 0. We're expecting in this set our PTSD score to be about 25. If we go from a depression score of 0 to depression score of 1, my new expected value of my outcome is going to be about 26, right? This is our slope, this is our intercept, and if we go through and scatter plot this out, this is what our data is looking like, right? Do we have any concerns about linearity in these data, Stephanie? No, pretty good, right? And we got for every unit increase in our depression score, we get a unit increase, expected unit increase in our outcome score, and all of that is maybe captured here in what we would refer to as our unstandardized solution. Yeah, Candace?
This is real data?
Yeah.
Okay.
Yeah. Yeah, so, yeah, I don't know, it just kind of popped out. I was like, oh, okay. I had to double check and tell you I'm not lying to you. This isn't made up. This is the real deal. So for every unit increase in BDI total score, we would expect a 1 unit increase in our corresponding DAB score. So, questions about sort of this very basic formulation of the GLM. This is sort of the GLM in its most basic form. Okay. We can also calculate standardized solutions within our GLM. Okay. Unstandardized solution has some clear interpretive utility, particularly if we're talking about something, we're measuring things that have meaningful units, right? If I'm talking about years of education and income, right? I'm talking with very concrete things that make sense, right? And so if my slope in that equation is, 10,000, right? For every year of additional education that I have, I can expect a 10, that might be a little bit big, but I can expect on average a $10,000 increase in salary. That unstandardized solution has real interpretive value because we're working with real stuff, right? However, when we're working in psychological science, a lot of times we're working with self-report measures or other instruments that don't really have any real meaning, right? I mean, sort of a score of 5 is bigger than a score of 3, but they're not like real units and things like those, right? And sometimes what we can do is create a standardized model. We'll talk about benefits of standardized models, but standardized models are nice because they allow us within a model to start looking at the relative strength of different predictors that we might have in the equation. For a standardized model, what we do, simple, all we do is we take all of our X scores, turn those into Z scores, take all our Y scores, turn those into Z scores, and then we just regress the Z scores of our outcome onto the Z scores of our predictor. This gives us a standard solution. Okay, standardized solution, our X's and our Y's are now on a common scale, and what's going to happen is in our standardized solution, these values, our X and our Y, our regression line is going to pass through the mean of X and the mean of Y. So when X is equal to 0, which is, if we're calculating Z-scores, what does it mean when we have a Z-score of 0? What does Z-score of 0 correspond to? What do you think, Stephanie? The mean, right? And our Z-score of Y is 0, which means the mean. So we've got the mean of X, the mean of Y, we've got that point right there. And what's going to happen is we're going to get a regression equation that runs right through there. So if we have an impact on our standardized solution, how is this equation different than the one we had previously? Yeah, it doesn't have an intercept, right? Because the intercept, the expected value of y when x is equal to 0, well, if we say 0 is at the mean, we're going to get 0 here. So, I mean, you could put 0 plus, but then that's not super useful, right? It's sort of redundant. And so what we don't have with our standardized solution is an intercept, because the intercept is always 0 in our standardized solution. If we run our standardized solution for these data, we get y hat equals 0.535x. Anybody tell me how do we interpret this slope? What do you think, Sam?
For every 0.5 times equals y.
Okay, so we're getting there, right? So relative to our unstandardized solution, what have we done with the standardized solution? What are our units now? Perfect. Okay. So Morgan, what's going to be our interpretation of our standardized or our standardized coefficient here?
So given a half standard deviation increase in x, we could expect a 1 standard deviation increase in y?
Close. Flip it around.
Okay.
For every standard deviation increase in depression, we're expecting about a half a standard deviation unit increase in our outcome. So the interpretation is the same. We're just thinking about now in terms of raw scores, we're just using standard deviation units. And so again, standardized coefficient, expected standard deviation change in y, given a standard deviation change in x. If we go through and draw our regression line, this is what we get. Alex, is our regression line, as we plotted out here, is this going to look different for our standardized and our unstandardized solution? No, it's going to be identical, right? So it doesn't matter. It doesn't change the strength of the relationship. It just puts us in a different metric that is more efficient for comparing different different predictors within a model, okay? And if we go through and we take a look for these data, standard deviation of our vector suppression inventory is about 12. Standard deviation for our PTSD measure is about 22, right? So looking back here, we would say for every 12-unit increase in our BDI, we would expect about an 11-point increase in our CAP score here, right? So we're just translating this over into standard deviations in this. Questions about any of this? And we'll get into this much more when we start to jump back into regression stuff. Okay, so for our bivariate GLM, we've got 3 different forms of specialized bivariate analyses. Just like we did last semester, when we're trying to figure out what type of analyses should we use, always, first thing to do is say, what are my inputs? What are my outputs? What's the level of measurement? If you answer those questions, your options are going to be sort of limited down to a set of appropriate analyses here, right? So if our x is continuous, our y is continuous, we can use a Pearson correlation, right? So if we've got a continuous x value, continuous y variable, and I want to look at the relation between those two things, I can run that with a Pearson correlation. If my x is dichotomous, right? It's either a 0, 1 variable, and my y is continuous, right? What are my options? What do you think, Stephanie? A t-test, absolutely, absolutely. What else could we use? Essentially a correlation, right? We call it a point by serial correlation, or we can use a t-test, right? These two things, so your t-test is just a special case of the GLM. It's just a special case of correlation, right? And we'll talk about how we can go back and forth between these two. And sometimes you get in arguments with co-authors about whether you can or cannot do this. I assure you can. It's the same thing, right? We're just determining how we're expressing our statistical test and making a determination at that point on what makes the most sense, sort of given the question at hand. So if I've got an IV that takes on a 0, 1 value, an outcome that's continuous, we can use a correlation, specifically points by serial, or our t-test. Right? What if we have 2 dichotomous variables, right? 0, 1, 0, 1. Alex, any thoughts on what we could use there? Chi-square, absolutely. Chi-square, or the measure of association here is going to be our phi coefficient, okay? Phi coefficient, just another specialized case of your Pearson correlation. So again, all of these quite interchangeable. It's just the way and the formula that we're going through and using to calculate these are going to depend on the level of measurement of my x variable, level of measurement for my y variable. Functionally equivalent. Only thing that differs with our GLM versus like a t-test or a chi-square is that we're focusing on relations as opposed to group differences. With our t-tests and our chi-squares, we usually talk about, with chi-square, we're talking about independence. Is there a dependency between yes, no on this and yes, no on that, right? Is there some sort of dependency? If we're talking about our t-test, we're talking about is this group different in their means from that group? And sometimes that's an appropriate way to talk about things. But know in the back of your head that we can just as easily talk about this in terms of relations as opposed to group differences. And some of the benefits of identifying this and talking about or thinking about even some of our means-based tests that we spent last semester talking about in terms of relations, we can start to incorporate increasingly complex models if we just break this down and start thinking about things in terms of relations, right? So I can, if I want to look at the impact of gender on income, right? I can say that men on average make higher mean wage than women, right? And that's evidence of wage inequality. But what I could also do is I can take that dichotomous variable and I can plug it into a regression equation where I'm looking at the impact of gender and education and sort of part of the country that you're living in, and take income and regress that onto all of those other things, right? Now we've got a gender variable within the context of a regression model, but then it starts feeling weird to talk about mean levels, even though we could, because that's not really the model we're looking at, right? But what we can do, instead of talking about mean differences, we can say, this is the relation between gender and our outcome, right? Same thing with ANOVA, right? If we've got sort of condition, even in an experimental setting, conditions 1, 2, and 3, looking at the differences in these experimental conditions on an outcome, we can say, well, this is average difference in means across these 3 conditions, or we can say this is the relation of condition to outcome, functionally the same thing. And so thinking about things in terms of our generalized linear model gives us a little more flexibility than trying to break things into groups and talking about mean differences. Okay. So again, using our GLM to start to expand and start talking about increasingly complex models, our simple multivariate generalized linear model takes our bivariate model and just starts to expand it, right? And so what we end up with is our expected value of y base is a function of the weighted sum of whatever predictors you have in your model, okay? So if we were to ask, what's the unique association of depression, trait anxiety, and social support with PTSD, right? So we took our previous example, we were just looking at the bivariate relation between depression and PTSD, and we're saying, well, maybe it's just not all depression, maybe there's other stuff that might be relevant in here, right? So we want to add in, as predictors, trait anxiety, social support, and regress PTSD onto those 3 predictors. Now all of a sudden, we have our, and if this is our standardized solution, we have the z-score of our outcome plus the weighted influence of our respective predictors. Okay? Now, Alex, if I'm looking, if these are standardized coefficients, which one of these has the strongest, at least in terms of absolute magnitude, the strongest relation with my outcome here? Depression still does, right? And how did you know that? Because it's bigger than the other ones, right? What if this was an unstandardized solution? Could I do that? No, right? Because I don't know what the scale is, right? If I've got something that's on a massive scale, that's going to give me a very different coefficient than a smaller scale. But when we use our standardized formula, we're putting everything on a z-score metric, right? And so what we're looking at here is the unique contribution that depression holds in relation to PTSD after we cut out everything that's shared across trait anxiety and social support. Same thing for our next 2 predictors. You'll see here very clear additive function, that assumption of your GLM, where we've got, okay, we're going to start out with the unique effect of depression, and then we're going to add whatever is left over that is contributed by trait anxiety, and then we're going to add whatever's left over associated with social support, right? So you've got each one of these going through and contributing sort of something above and beyond what's accounted for by the previous predictor. Questions about this? All right. Now in multivariate form, so this is, and again, you get, so some people will talk about multivariate statistics as, if you're talking about multivariate statistics, you're by definition talking about multiple outcome variables. Here, terminology we're using, if we're talking about a simple multivariate GLM, we're saying we've got a bunch of predictors, but just one outcome here. Now, the difference between our standardized coefficients in our multivariate, or a simple multivariate GLM, is that each one of these regression equations in our simple, in our just our bivariate GLM, we can interpret as a correlation, right? For this model here, my correlation between BDI and CAPS is 0.535. That's just the bivariate relation. That's a correlation coefficient in the univariate case. As we transition over to having multiple predictors, we can't now interpret these as correlations. These are no longer correlation coefficients. These are partial coefficients, right? These are indices of the extent to which these individual variables hold a unique relation with our outcome. So be careful about that. Sometimes people will try and interpret standardized coefficients in a multiple regression as correlation coefficients. They're absolutely not. We're going to take a lot of time focusing on Venn diagrams and sort of seeing where all the different variance goes through. But just recognize if you've got a correlation, or so if you're regressing an outcome onto one variable, that standardized coefficient is going to be by definition identical to correlation coefficient, right? You're just adding a, oh no, you're not adding an intercept in there. It's going to be identical in the bivariate case. But as soon as we start adding multiple predictors, unless those predictors are all independent of one another, correlated 0, right? These are going to be partial coefficients. And we'll get into more of the ins and outs of that as once we get into regression stuff. So for a simple multivariate GLM, we have multiple predictors, one outcome. If we have one if our x's are continuous, our y's are continuous, we're working with a regression model here. Okay? So I've got one continuous outcome, I've got continuous x variables, we've got a regression model. Okay? If I have a continuous outcome and I have a discrete predictor or a series of discrete predictors, what I'm looking at is an ANOVA model, right? If we're talking about discrete, we're talking about categorical predictors here, right? Again, identifying ANOVA, right? These ANOVA models that we were conducting before, these are just an extension or a special case of our generalized linear model. If I have a mixture of continuous and categorical x value or predictors and a continuous outcome, we might take a look at that in something along the lines of an ANCOVA. If I have a continuous set of predictors and a categorical outcome, we might be working with a discriminant function analysis or logistic regression. If we've got a mixture of continuous and categorical predictors and categorical outcome, we're working with logistic regression. And if I've got a mixture of continuous and categorical outcomes and our predictors, and our outcome is time to event survival analyses. You got some time series data here. If you look in your Tabachnik and Fidel text in one of the appendices, you've got kind of this big decision tree. Can be incredibly helpful in terms of you're trying to figure out, oh, what analysis should I use? Basically, it's following this pattern. This is where I pulled all this from. So you can say, what are my IVs? What are my outcomes? How many do I have? And that will help you start to narrow down some of your analytic options. Okay. So again, anytime you're confronted with a question about, we've got this and we've got this, and we want to look at the relation between those two things, right? Identify how many variables we have on the left side of the equation, the right side of the equation, determine level of measurement, and that should start to shoe you in on what we're looking at in terms of our options. Questions on any of this? Okay, so this is our simple multivariate GLM. But to this point, what are our current limitations, right? Limitations, ironically, similar to the ones we started out with at the very front when we're talking about our bivariate statistics, right? Sometimes our simple multivariate models can be cumbersome and inefficient, also can start to limit the types of relationships that we're looking at, particularly if I'm interested in multiple outcome variables, right? If I want to take a look at the relation between gender and college performance, a lot of different, what I might want to do is look at all of these outcomes simultaneously, right? And if I want to do this, this is when we're talking about our full multivariate GLM. Full multivariate GLM, we've got a bunch of predictors, we've got a bunch of outcomes, okay? I'm wanting to look at parental income and gender and major and age and how many brothers and sisters I have, whether or not I'm a single child or not, looking at all these different measures that we could say capture college satisfaction. So I've got a bunch of DVs, I've got a bunch of IVs, right? And what we're trying to do is mix these all together with our full multivariate GLM. So the difficulty, the conceptual leap when we go from our single multivariate models to our full multivariate models is that what we end up with, if we've got multiple dependent variables, sometimes we need to have multiple equations. So we don't just have one regression equation. We've got to have a number of different equations in there to start to sufficiently categorize the relations between our groups of x's and our groups of y's, okay? Think about this as solving an algebra problem with multiple unknowns, right? If I have x plus y equals 24, okay? Lauren, what's my value of x here? Could be anything, right? There's an infinite number of possibilities. What about y? Same thing, right? That's not terribly useful, right? I can't really estimate anything from that because there's an infinite number of possible solutions that I could have there, right? But if I go through and I say, okay, so I got that, but I know that I got 2x minus y equals minus 6, I got there, right? Now all of a sudden, things start to become more manageable, right? Now I've got two equations, right? And if these equations are both true, this starts to help me provide a unique solution, right? So I can say 3y equals 18, or excuse me, 3x equals 18, which tells me x is equal to what? 6, right? And if x is 6, what's y?
Oh, just kidding.
18. Okay. Okay. Now all of a sudden with these two equations, now I can start putting together unique answers and estimates for my x and my y value. Same type of thing going on with these multivariate solutions, right? I've got a number of different outcome variables, and so what I'm probably going to need to do is work with a number of different equations in order to capture the interrelations of my IVs and my DVs. Okay? So now the terms for these linear combinations, right? So we're still working with these linear equations, these linear combination of variables. But depending on what type of analyses that we're using, convention will call these different things, right? You'll sometimes hear these talked about as characteristic roots, principal components, right? But they're all referring to the same thing. It's just a system of equations that are capturing the relation between this set of IVs and this set of DVs, okay? And in general, what we have is as many roots, if we're calling these, we're going with roots, there are as many roots as the smallest number of x and y variables. So if I've got 5 predictors, and I've got 5 outcome and I've got 3 outcome variables, I have a maximum of 3 characteristic roots to go through and solve these outcome variables, right? So what we're looking here to determine the smallest number of outcomes is the smallest number of x and y, but the number of roots that we need to adequately account for our system of variables is oftentimes much less than the maximum amount that we have. Okay? So to try and give you kind of a visualization of what this looks like, let's say that we're looking at the relation between a number of predictors. I don't know how many we have, let's say 1 billion, to predict a pair of outcome variables, self-esteem and extroversion. Okay? So in multivariate space, we have self-esteem, we have extroversion here, right? And what I can do with just one characteristic root, I can capture and differentiate self-esteem and extroversion here, right? With this one equation, right? I can identify on this line where self-esteem is and where extroversion is with just this one equation, if this is how things are set up in multivariate space. Okay, and so I'm happy. So I could calculate 2 roots, but I don't need to because the one separates this and this, right? I say, okay, with this equation, this outcome is here, this outcome is here, I'm good to go. But what happens if we add a third outcome, social desirability? And if we plot social desirability in multivariate space, it's up here, okay? Now all of a sudden, can someone sort of visualize this and tell me what's wrong with my one characteristic root? Actually, your hand movements are telling me you're in the right direction here.
It's split between the two. It's no longer across.
What's that?
Really across two.
I'm sorry. What's that? I'm hard of hearing in the ear. What's going on?
You're only going like across.
Okay,
And
so
you're not accounting for it because like if they're on top of each other.
exactly,
you're-
exactly right. So can I differentiate between the position in multivariate states between self-esteem and extroversion in this with my one root?
Can you ask that again?
Can I differentiate between the position of self-esteem and extroversion with my one equation?
Yes.
Yeah. Can I differentiate the position of self-esteem and social desirability with my one root? Yeah, I
Okay.
can, right?
That's
Can I differentiate between extroversion and social desirability? I can't, right? So I've got 3 pieces of information, right, that I'm trying to figure out in multivariate space. My one root will differentiate this, and will differentiate this, but these 2 are indistinguishable without a second root, right? And so what I need in this system of equations, I need another equation to fully capture this. And so with my second root, between my first and my second, right, I can capture the difference between self-esteem and extroversion, and self-esteem and standard and social desirability. But then I need my second root to determine the difference between extroversion and social desirability on this second dimension. Okay. Now my second root, can I differentiate self-esteem and social desirability? Sure. Can I differentiate between social desirability? I can differentiate between social desirability and extroversion, but on my second root, I can't differentiate between those 2, right? Because they're sitting on the same plane. And so this is the idea how we might need to go through and incorporate a second root to account for sort of where these multivariate means exist in multivariate space. Now, if I remove, if social desirability happens to not be up here, it happens to be right down here, do I need that second root anymore? Nope, I don't, right? That's no longer needed because these all happen to line up along the same path. This one equation adequately accounts for, separates these 3 different entities in my multivariate space. But, so even though I can have up to 3 characteristic roots, just one adequately accounts for things, right? So thinking about in a practical application what this might look like, right? If this is sort of the analog of a factor analysis, right? Looks like I just need one factor to account for these 3 outcomes, right? Because they're all kind of lining up on their own. Here, I would need 2 factors, right? In order to calculate and differentiate and separate these things out. Okay? People kind of, and so don't get too worked up about this, but just trying to give you sort of a visual sense so that conceptually what's going on when we start talking about full multivariate models and things like that. Now, we're actually not going to do too much or anything at all with full multivariate models in this class. This class, even though it's called multivariate statistics, is a different, we're going to get on different things in this if you were to take multivariate through the statistics department. The statistics department is going to talk a lot about, yeah, they're going to do true multivariate models. But really, for psychological science, we don't use a lot of MANOVAs anymore, or DFAs anymore, or things like you don't just don't see them, right? And so, given that we only have 2 semesters for me to torture you all, we're just going to stick to single multivariate models for the most part. Okay. Questions on this? All right. So our fully multivariate GLMs, if we've got a group of continuous predictors and continuous outcomes, working with canonical correlations. We're working with a number of discrete or categorical predictors and a number of categorical outcome or continuous outcomes. MANOVA, MANCOVA, we've got principal components analyses, factor analyses, SEM types of stuff. Again, this is all pulled from that table in the back of Tabachik and Fidel. You won't need that for this semester because we'll obviously know what types of models we're working with. But if you get deep into the weeds and trying to figure out what I should be using to analyze what, that you make sure that you take a look at that as a resource. All right, questions? All right, welcome back, everyone. Hopefully you did your homework. You're up to speed. I don't have to explain this battle cat. It's a different person. The cringer is a different thing that goes through. All right. So what do we got? We got about a half hour left. Let's go through and jump in and start talking about correlations types of stuff. Right? Let's. So building on what we've just gone through and discussed in terms of RGLM, am I jumping ahead? Do people have sort of access to this stuff here? What's that? Angela, I get the sense that you're disappointed in me.
No, my PowerPoint's just not working.
Oh, okay.
It's okay.
It's a bad day for technology. This place has got gremlins in it or something. Okay. Are you good to go?
Yeah, I opened the PDF. We're good.
Okay, good
Thanks.
deal. All right. So we're going to start out talking about just basics of correlation here. None of this is going to be news, but wanting to, and from a technical standpoint, differentiate between correlations and regressions in terms of basic fundamental assumptions of these two analyses. If we're talking about correlations, we're talking about a measure of association, and this starts becoming important, between random variable X and random variable Y, okay? If we're talking about a random variable, what are we talking about? Anybody know? What do you think, Sam? Yeah, right. So the value can be the whatever the value is for this variable. It's sort of can be anything, right? Between the real limits of whatever that variable runs to across the real range of that variable. The value could sort of be anywhere in between there, right? So with the correlation, we're looking at the association between random variable X, random variable Y. And so we're working here with what we're going to call a bivariate normal model. And what we're doing is we're assuming sampling error in both X and both Y. We're going to get into this bivariate normal model, talking about, describe what we mean by that. But essentially with a correlation, we're saying, all right, we've got variable X, and variable X is going to be sort of randomly distributed across the individuals in my sample. And I want to look at the relation between this and some outcome variable Y, not even an outcome, just another variable Y, which can also have random scores across the expected range of that variable. And what we're assuming in our correlation, and sort of the fundamental basics of the calculation of our correlation, we're assuming that we have sampling error in our X and our Y. Okay. What is, somebody tell me what sampling error is?
The expected difference between the sample statistic and the confusion.
Exactly, right? So I go through and I measure your level of extroversion as this, right? But I know that's not a perfect, I'm going to be off a little bit, right? And so with our correlation, in our correlations, we're assuming that we've measured X with error and we've measured Y with error, right? Contrast this with regression. This is a statistical model where we've got a fixed variable X. In a technical situation, we're assuming that our X variable, our predictor, is a fixed variable, and we're using that fixed variable to predict observed values of random variable Y. Okay. Any ideas? Anybody have an idea on what we're talking about in terms of a fixed variable? Okay, this is a little bit tricky. We'll get into this more when we get into the regression. If I'm talking about a fixed variable, experimental condition is a fixed variable, right? I've got experimental condition 1, 2, and 3. You can't have experimental condition 1.5. You can't have experimental condition 2.7. It's either 1, it's either 2, or it's either 3. And it's not random. I'm assigning people where they go, right? This isn't just something that happens organically. I've deliberately said, for my fixed variable, for my variable experimental condition, this is a fixed variable where the values are either 1, they're either 2, or they're either 3. And that's it, right? So technically, within a regression model, we're assuming that our predictors are fixed variables, using to predict random variable Y, and we're assuming that our X variables are measured without error. Right? Our predictors in a regression model, the assumption is that these are measured without error, and we're using these to predict some outcome, random outcome variable Y, that we're tolerating error in that. Okay, does this seem confusing to people maybe in terms of how we typically use our regression models? It should, right? Because we are typically using a lot of times random variables X in our regressions and things like that. But we'll talk about sort of workarounds that we have in our basic assumptions to make sure that our inferences and our test statistics aren't biased. So again, but from a technical level, we're assuming only error variance or sampling error in Y when we're running our regression model. So again, this is our familiar plot of BDI scores and looking at depression and PTSD. If we go through and we run our correlation, we get a correlation of 0.535. This should seem familiar because this was also our standardized coefficient in our regression model that we ran, right? But if we run a correlation, we get a correlation of 0.5, which is going to be a strong correlation here. This is statistically different than 0. Our correlation coefficients are going to run from -1 to 1, okay? Now this is different than our standardized coefficients. Standardized coefficients in a regression model, they can technically exceed 1 sometimes, right? That doesn't happen a lot, but it can mathematically. It might cue you into some weirdness in your model, but again, these standardized coefficients being different than your correlations. Correlations bounded by definition from -1 to 1, and our values of our correlations indicating the magnitude of association and the direction, right? As we start getting closer to -1 and 1, we're getting a stronger correlation in terms of the absolute strength of the relation, our sign giving us direction here. Okay. Questions about this? This is straightforward, probably not news to anybody. Okay. This here, though, all right. Guess the correlation. So that's where So if we go to this, right? This is hours, wasting out. Don't look skeptical. Go ahead, try it. And so block off 6 or 7 hours because you spend the whole time. You only have so many lives,
What
right?
is this? Are you sending it to us?
Yeah, it's at the bottom of your. Is it not there?
No, it's not in the PDF.
Oh, okay.
It's just guessthecorrelation.com.
Yeah, right. It's hard. It's hard. You wouldn't think it. So you got to go through. You got to enter. This is where I had a score of 30, I guess, on this guy.
You can do 2 players.
Or no, I guess trying to jump over a hole in the ground. Right. On hell tried to show me up. He's like, oh, I did it. Whatever.
Of course.
a good time. Would strongly encourage you to take a look at that. Okay, so we're talking about correlations, right? One of the things we need to do in terms of jumping back into some of the stuff that we talked about last semester, just a refresher on variability. Okay, recall that variability in general is referring to the extent to which scores in our distributions are spread out or grouped together, right? Now we have different versions or different metrics of variability. We can talk about range, we can talk about standard deviation, we can talk about variance, right? But if our scores in our distribution are all the same, I have no variability. If they're really spread out, lots of variability. And again, thinking about always refreshers, thinking about variability in terms of describing your distributions in terms of distance, right? Thinking about, and if we're talking about standard deviation, right, because that's a nice interpretable metric of variability. How much distance to expect between two randomly selected scores, right? If I say standard deviation is 5, that's telling me if I go through and I pull 2 random scores out of this distribution, I'm expecting that on average those 2 scores are going to be about 5 units apart from one another. Or I can think about how far, think about standard deviation conceptually is on average how far any randomly selected score is going to be from the mean, right? If I just reach in the bucket and pull out a score, I'm expecting that on average this score will be about 5 units from my mean value, okay? Also tells us how much, variability tells us how much, well, an individual score, randomly selected score, is going to be representative of the entire distribution, okay? If I have low variability, what does that say, Katie? If I go through and I randomly select a score, I have low variability, should I assume that that score will be representative of the other scores or not representative of the other scores on average?
On average, representative.
It's more representative, right? Because if everybody in my sample is somewhere between 5'8" and 5'10", anybody who I pull is probably going to be pretty representative. If I'm going through and grabbing someone from anywhere from kindergarten to sort of adulthood, a lot more variability in height, right? So any one person I pull is not going to be, likely not to be terribly representative from people in general, okay? And so essentially what this is doing is telling you how much error to expect in our measurements, and sort of this being essential for our inferential statistics, okay? People clear on variability, sort of this is all sort of bringing back sort of fond memories of 50, 60. Excellent. Okay, variance, right? Recall that variance is our second population moment, right? Our variance is the average squared distance from the mean. Okay, so if I take the average distance from the mean, square that, we've got our variance. Standard deviation, again, loosely interpreted as the average distance of any individual score from the mean, or the average distance of any 2 scores from one another. If we think about calculating our variance, recall, first thing we do is we calculate a deviation score for each value. So we've got, these are our x's. We go through and calculate, subtract each individual score from the mean of that sample, gives us a deviation score. We then calculate the square of each deviation score. We take these and we square them. Why do we square them, Morgan?
So that they're all positive?
So that they're all positive. Because otherwise, what we need to do is once we've got those squared deviation scores, we add them up. If we just add up the deviation scores, what do we get, Angeline? 0, right? And so that's not helpful. So we square them, turn them all positive, add these up. This gives us our sum of squares, right? Sum of squares is going to be important because we're going to continue to use this. Sum of squares is just a different metric of variability. It's not a meaningful unit of variability. I can't sort of look at it and say, oh, that's a nice sums of squares there. I don't know what it means. Is it a lot? Is it not? I don't know. It just is, right? But what we can then do is take that sum of squares value, subtract it by n minus 1. And why are we subtracting, why are we dividing this by n minus 1 instead of the total number of scores in the sample? What do you think, Katie?
Degrees of freedom.
Degrees of freedom. And what is this helping correct for? Remember? What does this do to my variance if I divide my sum of the squares by n minus 1 versus n? in terms of making my variance bigger or smaller.
Makes the variance bigger.
Makes it variance bigger. And why do I need to make my estimate of variance bigger?
So it's more representative of the
Right,
population.
because we're never going to get all sort of the extremes adequately represent the extremes in our sample on average, because it's going to be rare to randomly select those, right? And so what we're doing is we're systematically correcting for underestimation of population variability with this simple correction, right? And so as our sample gets larger and larger, our opportunities to capture those people on the extremes goes up and up, right? And so we have to do less to correct for it. But if we've got a small sample, we're probably mostly going to be pulling from the middle of the distribution, and it provides a larger correction there. So we've got our variance, then going through taking the square root of our variance to get our standard deviation. And then we're down once again to a metric of variability that's meaningful in terms of thinking about units of distance within the context of this variable, right? So again, sums of squares, your variance, standard deviation, all measures of variability. It's just sum of squares and variance aren't terribly useful for just looking at it and making some sort of practical evaluation on stuff. Okay, and then we've got computational formula that we talked about. So this kind of conceptually what's going on, but this being a quicker, faster, easier way to calculate this thing. Okay, covariance. Now this is something that we haven't talked about. Covariance is just a metric providing an extent to which two variables relate to one another, right? And covariance calculated as the sum of, because we've got two variables here, the sum of our individual x's minus the mean of the sample, multiplied times the individual y's minus the mean of the y's divided by our degrees of freedom. And so if we think about this from an actual perspective, so we've got two variables, we've got depression and we've got PTSD. And I want to know the extent to which depression co-varies with PTSD scores. Okay? Now we've got a couple different scenarios. If I have large X values paired with large Y values, so I've got large X's paired with large Y's, what's going to end up happening is that some of the products of the deviation scores are going to be large and positive, right? So if, in general, big X's are associated with big Y's, right? So I'm looking at here. So this X value of, say, 50, so I've got 50 minus the mean is going to be 45 times 120 minus 20, right? I've got two large positive values, and so that's going to end up giving me a large positive covariance. Same thing if I've got within that same set all my small variables or all my small x's are paired with small y's, right? So I've got so this value of 0, so 20 something minus, or 0 minus 20 something gives me a negative number here, but also 0 minus 45 gives me a large negative number here. I'm multiplying two large negative numbers, which still is going to give me a positive covariance if this is what's going on here. Okay. However, what we can do if we have large X values that are paired with small Y values, some of the products of our deviation score is going to be large and negative. Okay. What are we talking about here, Sam? What's the situation we're hypothetically talking about? Yeah, right? So we're just talking about a negative covariance. So in this situation, my small x values, or my large x values here are paired with negative or small y values, right? So I've got stuff going on down here, and my small x values are paired with large y values, right? So what's going to happen is I'm going to get covariance still quite strong, because if I'm taking, 60 minus 20 something, that's going to give me a large positive value here, but I'm going to have 0 minus whatever, sort of 45 up here, that's going to give me a large negative value. What ends up going to happen is I'm going to have a negative covariance working right here. Okay. Now, when scores on my X are unrelated to scores on Y, sometimes my large X values are going to be paired with large Y values, and sometimes with small Y values, right? Same thing, sometimes my small X values are going to be paired with large Y values, sometimes with small Y values. And so what ends up going to happen is these cross products, some of them are going to be positive, some of them are going to be negative. They're going to cancel each other out, and what I'm going to get is some of my cross products, some positive, some negative, going to produce a covariance very close to 0 or something along those lines, which would indicate a non-relation between those two variables. Okay, so mathematically, this is what we're looking at in terms of our covariance. Covariance just being the extent to which X and Y vary with one another. Computer's going to fly away, I guess. All right. Computational formula for covariance. Again, conceptually, this is what's going on, but again, computational formula that'll make things speed up the calculation of this. Okay. So if we're talking about our Pearson correlation, okay, Pearson correlation is just a standardized version of your covariance. All right. Absolute value of your covariance itself is a function of the standard deviation of X and Y. Okay. So if we have, and this is why, if you hear, we need variability in our data to demonstrate the strong relations, right? We talked about in our means-based tests, our variability around our mean is being error, right? Because if I'm running group A and group B, and everybody's getting the exact same thing, everybody in group A should have about the same mean value of my outcome. Everybody in group B should have about the same value of the outcome, right? And if the extent to which they don't, that's error. That's stuff that we're not accounting for, right? And so we can maybe start to think about variance as a bad thing within that context. Within the context of correlation and regression types of things, we want large variability, because if everything is stacked on top of one another, it doesn't give us any opportunity to see that nice scatter plot. As things are getting bigger, X is getting larger, or Y is getting larger, and so our covariance that forms the foundation for our regression coefficient, direct function of standard deviation of X and standard deviation of Y. Okay, but sort of like variance, covariance doesn't have any sort of intuitive meaning to it, right? I can say, hey, this is the covariance between X and Y, and you say, cool, I guess now I know that, right? You can't draw any sort of real interpretation from this, but if we take that covariance, we divide it by the product of the standard deviations of X and Y, this is where we get our Pearson coefficient. So your Pearson coefficient is just your covariance estimate divided by the standard deviation of X, standard deviation of Y, gives you a nice correlation coefficient bounded by -1 and 1. Okay. One thing to recognize, we talked about this previously last semester, this idea of unbiased estimates. What are we talking about if we're talking about an unbiased estimate? Angela, what are if I say this test statistic is unbiased, what does that mean?
No external factors.
What's that?
I mean, not like that. No external factors are.
Okay, kind of getting there. If I say that this this test statistic is an unbiased estimator of the population parameter, what does that mean?
Like it cannot directly.
What's that?
Estimate I'm not sure.
Okay. Anybody sort of reaching in the Wayback Machine remember what we're talking about unbiased estimators? Yes.
The average.
Yeah.
Equals the population.
Perfect, right? So sort of like a mean is an unbiased estimator of the population mean. Now some of our sample means are going to be bigger than the population estimate, some of them are going to be smaller than the population estimate, but on average, the sampling distribution of the mean is going to equal the population mean, okay? Now, our correlation coefficient, so if I were to take the sampling distribution of my correlation coefficient, with small samples, particularly with small samples, your Pearson correlation is not going to be an unbiased estimate of your population coefficient, right? It's going to be systematically be too large, right? And we need to make a downward adjustment of that. And so, particularly when we're dealing with small samples, our Pearson correlation isn't an unbiased estimated of the population association. And so, if you're working particularly with small samples, we've got a formula for an adjusted R coefficient here, where you're going to go down through and multiply or sort of divide it, and it's going to sort of downgrade that a little bit based on the number of people in your sample. Okay. So similarly, people remember talking about, or when we presented Hedges' unbiased G. You remember that? And again, sort of the concern that our standard effect size, or our effect size G, is going to be too big when we have small. It's going to overestimate the population effect when we're working with small samples. Same situation that we've got here with our Pearson correlation. Questions about this? All right. Testing the significance of our correlation coefficient. Null hypotheses. This is not P, this is rho. But we're saying rho equals 0. We're saying the association of the population is 0. Now don't use this in assignments. Tell me what the actual population is, or I'll take a point off. And those things add up, right? But so we would say that the association between X and Y and sort of the specific population is equal to 0. We would say that X and Y are linearly independent within whatever population we're talking about. Our alternate hypothesis is that this coefficient is some non-zero value, right? This is a non-directional hypothesis. We're not saying it's going to be bigger or smaller. It's just going to be some value that's not 0, right? Thank you. That was my point. Okay. Now, what we find is that for our significance test for our Pearson correlation, sampling distribution of R, assuming a null correlation, assuming the population association is 0, the sampling distribution for our Pearson correlation follows a t-distribution with n-2 degrees of freedom. This is super convenient. This is nice, right? Because we already have talked about at length the sampling distribution, or t-distribution. We know the t, we like the t, we think the t is a pretty good deal, right? If we were to, say, look at the relation between X and Y in this population, and we went through and drew in infinite numbers, all possible samples of 50 from this population that could be drawn with replication, and we plotted out the correlation coefficients for all possible samples of 50, we would find that that distribution of correlation coefficients follows a t-distribution with n-2 degrees of freedom. And so what we can then do, once we calculate our correlation coefficient, we can then run a hypothesis test on this using our t-statistic. And we do that by saying our test statistic is equal to our correlation coefficient that we've calculated, multiplied by the square root of our sample minus 2 over the square root of 1 minus the square of our correlation coefficient. This is going to give us our test statistic that we can then go through and compare against a critical value of t with n-2 degrees of freedom. Okay? Simple, easy, all the stuff that we talked about last time makes this easy. For this, we're probably not going to be using t-tables. Probably be using our p-value calculator that we use online, right? But very easy, so once we've calculated that correlation coefficient, to then go through and run a statistical test to say, do we have sufficient evidence based on what we've got from this sample to conclude that the relation between X and Y and whatever population we've sampled from is some value that's different from 0. Okay. Is this ringing bells making sense to folks? Okay. Finish up with effect size. Our Pearson that we're testing and running the our hypotheses test on is also a fantastic correlation or effect size, probably the most common effect size we see out there. This is what we often will reduce other measures into if we want to run meta-analysis and things like that, okay? Small R of 0.1, small, medium, large. Again, this provides us a basis for evaluating the magnitude of the relation between X and Y. And what we can do, which is nice, we can run a straightforward transformation between R and D, right? So if I calculate a Cohen to D, or excuse me, if I have a Pearson correlation, I can translate that into a D metric if I want to, right? I can also calculate an R into a D if I want to. Now, once again, sort of my decision on what effect size to report is going to be based on sort of the question at hand, right? So if I'm looking at a t-test, right, and I want to know sort of the effect, the absolute magnitude, or the magnitude of the difference between group A and group B, if I'm running a t-test, then I'm probably going to just stick with a D, right? Because that's a meaningful interpretation. I can say that sort of group A is X number of standard deviations on average above group Y, right? But if I would need to go through, say I've got a study here that's reported their effect size is an R, and this one that's reported as a D, I can move and translate those back and forth pretty easily. Other metric of effect that we can calculate here is R squared. So if we take that Pearson correlation, right, and we square it, we can now interpret that squared correlation, the proportion of variability in our outcome that's attributable to variability in X, right? So I go through and I square this and I get a R, so let's say I got a correlation of 0.5, and I square that, I get an R square of 0.25. I can say that approximately 25% of the variability in my outcome is directly associated with, or attributable to variability, or associated with variability in X, right? So this is where we start to see the basis for our multiple R and regression and things like that. We're accounting for about, in this situation, about a quarter of the variability in our outcome by just knowing what my X. If I know what my X values are, I can sort of account for about a quarter of the overall variability in my outcome, given a correlation of X and Y of 0.5. Okay. Good place to stop. All right. Questions about any of this to this point? We've been moving through this pretty quickly, but I'm assuming that most of this stuff is fairly familiar, things that people have been exposed to previously. All right. Thanks, folks.